Welcome to section 12.6, where we're going to explore scattered plots, correlation, and regression lines. So far in this chapter, we've been analyzing single variables such as test scores, temperatures, or ages. But in the real world, we often want to know if two variables are connected to each other. For example, does studying for more hours actually lead to higher test scores? Is there a relationship between someone's age and their blood pressure? Do taller people tend to weigh more? Is there a connection between temperature and ice cream sales? These are the kind of questions that scattered plots, correlation, and regression lines help us answer. They reveal relationships between two variables, and that's exactly what we're going to learn how to do in this section. So let's get started. Objective 12.6.1, creating scattered plots. So what is a scattered plot? Well, first up, scattered plots. A scattered plot, also called a scattered plot or scattered diagram, is a graph that displays the relationship between two variables. Here's how it works. Each point on the graph represents one person or object in your sample. The x-coordinate represents one variable and the y-coordinate represents the other variable. Think of it like this. If we measure both height and weight for 10 people, you'd plot 10 points on your scattered plot. 1 point for each person showing their height on the x-axis and their weight on the y-axis. So how to create a scattered plot? Well, creating a scattered plot is actually pretty straightforward, and there are 4 steps. The first step is to collect paired data. Okay, paired data. So this means you need 2 measurements for each person or object in your sample. Step 2, you set up your axes. So you need to decide which variable goes on the x-axis, that's the horizontal one, and it's usually the independent variable, and which variable goes on the y-axis, which is the vertical one, usually the dependent variable. Step 3, we're going to plot each data pair as a point. So we'll move right to the x value, then move up or down to the y value, and then place a dot at that location. Step 4 is to label your axes and give your graph a title so anyone looking at it knows what they are seeing. So in our example here, we are asked to create a scattered plot for the given data. Okay, so our x values are 3, 2, 5, 1, and 3, and the corresponding y values are 5, 6, 9, 3, and 8. To plot this, we'd plot the point 3, 5. So this right here, this ordered pair gives us the point 3, 5. So I would go to 3 on my x axis and then go up 5. And that's this dot right here. Then I would go 2, 6. So I'd go to the right 2 and then up 6. Then I'd plot 5, 9. So I'd go to 5 on the x, up to 9. That's this point right here. Then 1, 3, go over 1, up 3, plot that. And then finally 3, 8. 3, 8. Okay, so each point represents one pair of data values. Once all 5 points are on the graph, then we can start to see if there's any pattern or relationship between the x and y. And that brings us to our next objective. All right, interpreting correlation. So what is a correlation? Well, correlation describes whether two variables are related, and if so, the strength and direction of that relationship. So when we look at a scattered plot, we're asking 3 key questions. First, is there a relationship? Do the points follow some sort of pattern? Second, what direction is the relationship? Is it an upward trend or a downward trend? And third, how strong is the relationship? Are the points tightly clustered or are they loosely scattered all over the place? So let's break down the different types of correlations you might see. So first one is a positive correlation. A positive correlation means that As one variable increases, the other variable also increases. Visually, you'll see the points trending upward from left to right. Some examples of positive correlation are hours studied versus test scores, meaning the more study time usually means higher scores, or height versus weight. Taller people tend to weigh more, or age of a car versus miles driven. Older cars typically have more miles on them. The next type is negative correlation. Now, a negative correlation is the opposite. So as one variable increases, the other variable decreases. So visually, the points tend downward from left to right. Some examples of these could be temperature versus heating costs. When it's warmer outside, your heating bill goes down. Or age of a car versus the resale value. Older cars are usually worth less. Okay. The third type is no correlation. So sometimes there's just no correlation at all, where the two variables aren't related to each other. The points on the scattered plot will be scattered randomly with no clear pattern. Some examples of these could be shoe size versus test scores. There's no relationship there. Or hair color versus math ability. The two are completely unrelated. All right, so strength of the correlation is next. So we looked at the different types. Now we're going to look at the strength. But correlation isn't just about direction, it's also about strength and how closely the points follow the pattern. And we have three different types of strengths. The first one is a strong correlation, which means the points cluster tightly around an imaginary line. The relationship is very predictable. If you know one variable, you can make a good prediction about the other. The next is a moderate correlation, and this means that the points follow a general trend, but there's some scarcity, meaning the data points are kind of scarce around the graph. So there's a relationship, but it's just not perfect because the points are scattered. Other factors also play a role in a moderate correlation. A weak correlation is the third one. Okay. And this means that the points are very scattered with only a slight pattern. The relationship is barely detectable. Knowing one variable doesn't help you much in predicting the other. Okay. Now, a regression line is going to be the next topic that we are going to move forward with from correlation. So now when we look at a scattered plot with a clear pattern, we often want to draw a line through it that represents the pattern. And this is called the regression line or the line of best fit. All right, just as you see here, we have points that have a positive correlation, and sometimes we want that line that represents that pattern. So the regression line is a straight line drawn through a scattered plot that best represents the overall pattern of data. It minimizes the total distance between the line and all the data points. Think of it like this. If you had to draw one straight line that came as close as possible to all points on your scattered plot, that would be the regression line. The regression line slopes upward for positive correlations, slopes downward for negative correlations, and is approximately horizontal when there is no correlation. Okay. So here's the really useful part. You can use the regression line to make predictions about values that aren't even in your data set. Okay. And that comes into our next concept, the correlation coefficient. So to measure correlation precisely, we use something called the correlation coefficient, represented by the letter R. The correlation coefficient is a number that measures both the strength and direction of a linear relationship between two variables. And here are the key factors about R. Well, R ranges from -1 to +1. R equals +1 means a perfect positive correlation. So all your points fall exactly on an upward sloping line. R equaling -1 means a perfect negative correlation. all points exactly on a downward sloping line. When R equals 0, this means that there is no linear correlation, so there's no relationship at all. The closer R is to positive or negative 1, the stronger the correlation. The closer R is to 0, the weaker the correlation. For example, if R is around 0.9, that's a very strong positive correlation. If R is around negative 0.8, that's a strong negative correlation. And if R is around 0.3, that would be considered a weak positive correlation. Okay, and this visual here in your notes kind of breaks down what would be considered moderate, what would be considered weak, no correlation, and then negative and positive. Remember, the more scattered the points, the correlation then does not exist. So there would be no relationship. All right, objective number 3, computing the correlation coefficient. So now, while calculators and software typically compute R for us, understanding the process helps you appreciate the correlation coefficient actually represents. So when you're computing the correlation coefficient by hand, you organize your work in 5 columns. The columns are x, y, x times y, x squared, and y squared. Then you find the sum of the numbers in each column and substitute those values into the formula for R. Okay, so this image here gives us the formula for R, where we have 8 terms that we have to find. Okay. N is going to represent the number of data points. The sum of x is the sum of all x values. The sum of y is the sum of all y values. Sum of xy is going to be the sum of the product of x and y. Sum of x squared is the sum of the squares of x. Sum of y squared is the sum of the squares of y. Sum of x squared is the square of the sums of the x values. So we would take this sum and we would square it. The sum of y squared is the square of the sum of all the y values. So we would take the sum of the y values and then square it. Okay. All right, let's use the sample data we have had before. So we have our x values here, 3, 2, 5, 1, and 3, y values 5, 6, 9, 3, and 8. Okay, and we're asked to find the correlation coefficient R. So step 1 is to create the 5-column table. So in the first row, we are going to have x is 3, y is 5, then x times y would be 3 times 5, which is 15. X squared would be 9. And then y squared, which would be 5 squared, which is 25. So x, y, x squared, and y squared. Then we would take the second row, which is 2 and 6, which would give us 12, 4, and 36. And we will continue that process through all the other ordered pairs. So 5 and 9, 1 and 3, 3 and 8. So now that we have all the x's, y's, xy's, x squared, and y squared, we now want to find the sum. So we're going to add up each column. So the sum of x is 14, the sum of y is 31, the sum of xy is 99, the sum of x squared is 48, and the sum of y squared is 215. Step 2 is to identify the values we need for the formula. So we have n equaling 5 because we have 5 ordered pairs. So that's the number of data pairs that we have from our table. We can calculate the sum of x squared, which is 14 squared, which equals 196. And we can calculate the sum of y squared, which will be 961. In step 4 now, we are going to substitute everything into the formula for r. So the formula for r has n times the sum of xy minus the sum of x times the sum of y in the numerator. So that's going to be 5 times 99. So this should be a 5, not a 99. 5 times 99 minus 14 times 31. And this then would give us actually 495. So we would change this 990 to 495 minus 434, which would give us 61 in the numerator. For the denominator, we have the square root of two quantities multiplied together. So the first quantity is n times the sum of x squared minus the quantity sum of x squared. So that's 5 times 48 minus 196, which is 240 minus 96. So this 480 should be 240, which then equals 48. So this 284 should be 48. Not 48, sorry, 44. Yeah, 240 minus 96. Yeah, 44. 44. And then the second quantity is n times the sum of y squared minus the quantity sum of y squared. So that's 5, it should be a 5, times 215 minus 961, which equals 114. Okay. So we can then take the square root of 44 times 114, which is the square root of 5,016, which is approximately 70.82. So finally, we then can calculate r. So we would take the 61 divided by the 70.82, which then should give us 0.86. Or if we round to 2 decimal places, it's about 0.87. Okay. All right. So what does r equaling 0.87 indicate? Well, this indicates a very strong positive correlation because the value is very close to a positive 1, which means that as x increases, y strongly tends to increase. The data points are clustered tightly around an upward sloping regression line, and knowing the x value gives you a good prediction of the y value. And that's the power of the correlation coefficient, because it gives you a precise measure of how two variables are related. Objective 4, finding the regression equation. So, all right, now that we can measure correlation, let's learn how to find the equation of the regression line. The regression line, which is the line of best fit we talked about previously, has an equation just like any other line, and it's y equals mx plus b, where y is the predicted value of the dependent variable, m is the slope of the line, x is the value of the independent variable, and b is the y-intercept where the line crosses the y-axis. And this is the exact same format as any linear equation we've worked with before. Now, to find m and b, we have specific formulas. The slope m equals n times the sum of xy minus the product of sum of x times the sum of y, all divided by n times the sum of x squared minus the quantity sum of x squared. The y-intercept b equals the sum of y minus m times the sum of x, all divided by n. Notice that the numerator for the slope formula is exactly the same as the numerator we used when calculating r. So if you've already found r, you've done part of the work. So let's find the regression line equation for the same data set we previously worked with. So we have our 5 data points. We found our x, y, x squared, and y squared sums. All right, so we know 5 is n. The sum of x squared is 196, and the sum of y squared is 961. So the first thing we're going to do is calculate the slope. So m equals 5 times 99 minus 14 times 31 all over 5 times 48 minus 196. So that's 495 minus 434 over 240 minus 196. So that's 61 over 44, which equals 1.39. Next, we calculate the y-intercept. So that's b equals the sum of y minus m times the sum of x. So that's 31 minus 1.39. That's what we got from step 1 times 14, all divided by n, and n is 5. So that gives us 2.31. Then we can write our equation. So now we just plug in m and b into y equals mx plus b, and our regression line equation is y equals 1.39x plus 2.31. And here's where this becomes really practical, because we can use this equation now to make predictions. Okay. For example, if x equals 4, we can predict y by plugging it in for x. So y would equal 1.39 times 4 plus 2.31, which would equal around 5.5 something, I believe, plus 2.31, which will equal 7.8 or 0.9 approximately. So when x is 4, we can predict y will be about 7.8, 7.9. And that's pretty cool, right? So now let's talk about what the slope and y-intercept mean, because you'll need to know that. So our slope here is 1.39, and this tells us that for each 1 unit increase in x, y increases by approximately 1.39 units. That's the rate of change. Okay. The y-intercept, which is the 2.31, that tells us when x equals 0. The predicted value of y is 2.31. So when I substitute 0 in for x, my y is going to be 2.31. So that's where the line crosses the y-axis. Now keep in mind that the y-intercept may not always have a practical interpretation depending on the context of the problem, especially if x equals 0 doesn't make sense in that situation. Objective 6, statistical significance. So here's an important question. When we calculate R from a sample, how do we know if there's a real correlation in the entire population? Or could our result just be due to random chance in our particular sample? This is where statistical significance comes in. Mathematicians have created tables of critical values that tell us whether our sample's correlation coefficient is strong enough to conclude there's a real correlation in the population. The critical value depends on 2 things. First, your sample size, n. Larger samples actually need smaller R values to be significant. That might seem backwards, but it makes sense because with more data, you can be more confident even with a weaker correlation. And the second is your significance level, which is represented by the Greek letter alpha. And this is how much risk you're willing to take of being wrong. So there are two common significance levels. The first one is alpha equals 0.05, or the 5% significance level. This means that there is a 5% probability we'll conclude there's a correlation when there actually isn't one in the population. This is the most common significance level used. It gives us 95% confidence that our conclusion is correct. Alpha equaling 0.01, or the 1% significance level, is the other common level. This is more stringent because there's only a 1% probability we'll be wrong. So that gives us 99% confidence that our conclusion is correct. So how to use critical values. So here's the process. The first is to calculate R from your sample data. Then you're going to find your sample size n in the table of critical values, and you will then look up the critical value for your chosen significance level, whether it's 0.05 or 0.01. And this table is located in your text. Then you will compare the absolute value of R to the critical value. After that, you will then make a decision, and your decision rule is simple. If the absolute value of R is greater than the critical value, we can conclude there is a correlation to the population. If it is less than or equal to the critical value, we cannot conclude there's a correlation. It could just be due to chance. So let's look at our example from earlier. We found that R equals 0.96. We actually found out it equaled 0.87, but let's just go with it. It's around the same value. With n equaling 5, which is our data pairs, can we conclude there's a correlation in the population at the alpha equals 0.05 level? Well, we have R equals 0.96 and n equals 5. So if we look up a critical value for n equaling 5 at alpha equaling 0.05, we find that our critical value is 0.878. So we would then compare in step 3 these two values. The absolute value of R is 0.96, and is 0.96 greater than 0.878? Yes, it is. So since 0.96 is greater than the critical value of 0.878, we can conclude that a positive correlation exists in the population at the alpha equals 0.05 significance level. What this means is we're 95% confident that the positive correlation we observed in our sample reflects a real positive correlation in the entire population. Okay, let's try another one. So suppose we found R equals 0.79 with n equaling 10 data points. Can we conclude that there's a correlation at both the 0.05 level and the 0.01 level? So we have R equals 0.79 and n equals 10. That's our step 1. Step 2, we'll look up the critical values for n equals 10 in our table. At alpha equals 0.05, the critical value is 0.632. And at alpha equals 0.01, the critical value is 0.765. So we will compare the 0.25 critical value to 0.79. And 0.79 is greater than 0.632. So yes, that's significant at the 0.05 level. Then we'll compare the 0.01 critical value. So 0.79 is also greater than 0.765. So yes, it's significant at the 0.01 level. Okay. So we can conclude then that there's a correlation at the 0.05 level. That's a 95% confidence. And we can also conclude that there's a correlation at the more stringent 0.01 level, and that's a 99% confidence. So the correlation is significant at both levels, which gives us a very strong evidence that a real correlation exists in the population. Okay. Just a few things to remember about statistical significance that I want to make sure you know. The first one is that we always use the absolute value of R when comparing two critical values, and this works for both positive and negative correlations. Okay. The second is that larger samples need smaller R values to be significant. And that's because with more data, we can be more confident about our conclusions because our sample is going to be more representative of our population. And the third, alpha equals 0.01 is more conservative than alpha equaling 0.05, and it requires then stronger evidence. Okay. And let's see, the fourth thing I would say is just because a correlation is statistically significant doesn't necessarily mean it's strong. Like a weak correlation could still be statistically significant if your sample size is large enough. Significance just tells you the relationship is real, not necessarily that it's strong. Okay. And finally, even if the correlation is statistically significant, it still doesn't prove causation. Um, just note that correlation does not equal causation. Like there could be other explanations for why two variables move together.